All right, let's solve this problem. I think it's a pretty good problem from the Hull book, which summarize everything that needs to be known concerning the fundamentals of the Black-Scholes model, especially the Black-Scholes equation. You can try to do the equations as I'm doing them, or put pause on the video and then check the answers. But we'll go through them one by one. So first one, what is n prime of x? Well, n is the cumulative distribution of the normal distribution, right? So n of x is the probability that you are below the value x. So for example, I showed it in the last video, but okay, this is not a normal distribution, but here is x. The area under this curve is n of x. So what is n prime of x? Well, n prime of x is exactly the equation for this curve. So it's this formula um, of x squared. Because we assume, so usually there should be sigma and mu. So would be minus mu here and, well, sigma squared and sigma inside the square root. But here we're not in this situation. Um, so yeah, just this. It is n prime of x. Okay, so first question, quite easy. Okay, so let's do the second question. Using the first question, then we'll show that the stock price times n prime of t1 is equal to the discounted value of the strike times n prime of d2. So these are all equations that we will use later to solve one by one all the equations. Anyway, so when we do these, we have s n prime of d2 minus sigma squared root of t minus t. So this is a simple relationship that links d1 and d2. And once we develop everything, then we use first question, of course, and we have minus d2 plus sigma square root of t minus t squared divided by 2. And why do we do this? Well, because we want d2, right? So when we want to move from d1 to d2, well, there's only one equation that links the two of them. So this is what we write. Let's keep going. This is now s over square root of 2 pi exponential of minus d2 squared over 2 plus, and then here we use the uh, remarkable identity, so 2 sigma square root of t minus t d2 plus sigma squared t minus t. And this is divided by 2, of course. And what this will give us is, here we can recognize n prime of d2. Okay, and now we will use the equation for d2, because this will give us s n prime of d2 times exponential of 1/2 of 2 sigma square root of t minus t. But d2, we remind the equation here, is divided by 2, so the 2 cancels each other, and the sigma square root of t minus t can cancel each other also. So we have ln of s over k, and yeah, everything else cancels out, plus r minus sigma squared over 2 t minus t plus sigma squared over 2, not over 2, plus sigma squared t minus t. But yeah, you see why it's going. Basically, the s here and the s inside the exponential will cancel out. So we will get n prime of d2 exponential of, oh yeah, there shouldn't be 1/2 here. Okay, and then we'll get the S, then K over S. There should be a minus only, that's why. Yeah, and that's where it's coming from. And then exponential of, okay, and there should be a 2 here. And so these terms and these terms are canceling each other, and then we get minus r t minus t. Yep, so this is the equation we wanted to have. Okay, third question. So the derivative of d1 with respect to s, this one is quite straightforward because there's only one part that has an s inside of it, so ln of s. So it's just 1 over s sigma square root of t minus t. Because d1 will be ln of s over k divided by this, plus something that does not depend on s. Okay, so we're good. And d2 over s is exactly the same thing. So they are both equal to each other, d1 over ds. So this will be also very useful, and as we'll show right after. Now let's go to the next question. Yeah, we want to show this, the derivative of c with respect to t. So this one will be a little harder because both d1 and d2 depends on t. So we will use the chain rule, and this can be written as s, then n prime of d1, d1 divided by t, with respect to t. And here minus, and here there's two terms. So the first term will be k exponential of minus r of t minus t. And we derive the t from here, so then we'll get a plus r, because the r is going out, n of d2, minus, and this one, k discounted, and exactly as above, and prime of d2, d2 over dt. Yeah, so this one can become quite messy, quite fast, but it's only a matter of organization. Okay, this is a minus here. I was having some problems. Why? Because there are 3 minus. The first one is here, the second one is here, and the third one is here. So minus, 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 and it gives a minus here. Then how we will do to solve this question, we can either compute all terms one by one, or we can realize we are at question D, and so we will use the question from before, which means we'll use in particular question B, which replace, where's my pen here, okay, and which replace the first part of the equation. So we have k exponential of minus r t minus t n prime of d2, and we still have the derivative of d1 with respect to t. Then I will use this one, this term, because it's exactly the same, t minus t n prime of d2, derivative of d2 over dt, minus r exponential of this term n of d2. And what we see is that we can factorize, of course. So we have k exponential of minus r t minus t n prime of d2. Okay, n prime of d2. And we have d1 minus d2 over dt. But we already showed minus this term. of D2. Now you might be tempted then to say that these are both equal, but it's not the case because remember, what are equal are the derivative with respect to S, not with respect to T. So how do we do that? Well, we use the other equation. We use the fact that D1 minus D2 is equal or is equal to sigma square root of T minus T. So this is the relationship between the two. Therefore, if you take the derivative of the difference with respect to T, then you can compute what it is. And so if I rewrite this with the power, then it's easier to deduce that the solution is sigma over 2 t minus t to the power minus 1/2, which gives this result. So with this parenthesis, we can continue our equation. So I recall that it's d of c with respect to d of t. So we have k exponential of minus r t minus t and prime of d2 sigma over 2 square root of t minus t minus r k exponential of minus r t minus t n of d2. And now we're very close to the result because this term we have it already by replacing with the question B. And this term we have it also here. So yeah, we just need to replace these. What is it? K exponential n prime of d2. So all of these is equal to s n prime of d1. And this gives the exact result for question D. So let me erase all of it and we'll keep going. Okay, so I don't need to write the results because everything is written already on the exercise page. So we're now at question E, D of the C with respect to S, and now we will use question C, of course, because we have this time with respect to S. So what happens when we derive C with respect to S? The first term, well, we can't just write n of d1 because d1 depends on s, of course. So we have n of d1 plus s, and again here, and prime of d1 with the chain rule, d of d1 divided by s, and then minus k exponential of minus r t minus t, and here again chain rule, and prime of d2, d of d2 with respect to s. And here we are going to use exactly here the question B again. So I can already erase it to not write too much and write the k exponential of minus r t minus t and prime of d2. And here you will see that these are the exact same factor terms, and these two are the exact same value also. So it's very simple. All of this gets cancelled. And so in the end, the result is indeed n of d1. But you need to make sure this is a famous mistakes that we can make because it's very tempting to say that because C is S times ND1 minus this question, if we don't see the fact that D1 and D2 depends on S, then it's easy to miss and to say that the derivative is just N of D1, which is correct, but incorrect in the other way because you didn't quite understood how to get here. So it's just, let's say it's correct, but only with luck. So it's not what we want. We want to make sure that we know that D1 depends on S and D2 also, and of T and of sigma for maybe other exercises. But anyway, this question is quite straightforward once we calculated these two terms and that they are exactly equal. So let's move up to question F now. Question F, which tells us to show that C satisfies the Black-Scholes differential equation. So for this, it's again quite straightforward. we just need to do all the computations. First, let's compute the second derivative, because we know it's only the derivative of nd1. So of course, here now you cannot say that nd1 does not depend on s, of course, because then you would get 0, but it's not the case, of course, because n of d1 is n of all of these value. So you cannot say, so now you cannot say it depends on, it doesn't depend on s, because you would get 0. Instead, you need to use the chain rule again. So let's just keep it at n prime of d1. And then if I remember correctly, it was 1 over s sigma square root of t minus t. Yep, we'll keep it like this. Now we'll compute the other term, the derivative with respect to t, we have it, and the derivative with respect to s, we have it. So now we replace everything. We write the Black-Scholes equation. So the derivative of c with respect to t, we have this term from question D. I'm just copy pasting what I see, sigma divided by 2 square root of t. Now it's plus rs from the Black-Scholes equation times the derivative with respect to s. And now it's plus sigma squared s squared divided by 2, and the second derivative, which is n prime of d1 times 1 over s sigma square root of t minus t. Okay, and now we need to simplify all this to just get r times c. Well, we are quite lucky, of course, because everything cancels out perfectly. Okay, let me erase it. The 2 here cancels with the s and the sigma also, so all the square disappears. And then we have s sigma over 2, 2, everything. So these two terms literally cancels out. And so we only have r, and we can put it in factor, and you will get exactly c, which is quite fantastic, because it's exactly what we want. So it solves the Black-Scholes-Merton differential equation. And now we'll just go to the last question. Let me erase it. So question G, show that C satisfies the boundary condition for European call option as T tends to big T, the maturity. So how do we do this? Well, we just need to compute limits. So we use the formula here. C equal S n of d1 minus k exponential of minus r t minus t n of d2. So what is the limit of d1 when t tends to big T? Well, I'll let you do this, but based on this formula, the first term, if we divide by sigma, this tends to, square root of t minus t tends to 0. So if you divide by something that tends to 0, well, it goes to infinite. And the second term just goes straight to 0. So it goes to plus infinity. And the limit of d2 when t tends to big T is also plus infinity for the same reason. Therefore, how does that help us? Well, we can get the limit for n of d1, because if you recall, this is the cumulative distribution function for the normal distribution. So if d1 tends to infinity, so it's like as if you take a d1 all the way here and then keeps moving to the right, and you compute the curve, the area, sorry, under the curve, then it tends to 1. So this is how you can see it when when t tends to big T, or when d1 tends to plus infinity. And this is exactly the same for n of d2. So this tends to 1, this tends to 1, this tends to 0. So exponential of 0 is also 1. So the limit when T goes to maturity of C is equal to S minus K, which is exactly the payoff of a call option. So yep, this is the end for this video. Funny thing to do is to make sure the same results apply for a put option. But yeah, these are the most basic question one can ask about the Black-Scholes equations. Um, this is, let's say, part one before diving into the deeper questions of the formulas, the equation. But yeah, so I know these videos are quite messy because it's my first few videos and I'm mostly doing them for myself for now, just to make sure I can do this during an interview, for example. So this is by teaching, I believe that you uh, remember the best and that you learn the best. So that's why I'm doing this. I'm forcing myself to teach to anyone. So yeah, this is quite messy, but don't worry, it will get better and better as I upload more videos, of course. So yeah, this is it for this one and see you in the next one.